Welcome back, and this is the Chipmaster, and we're going to continue from where we left off in the last class, and we're going to continue where we left off. So as I said before, we were at the charging chip, and the charging chip is used to control the production of PP bus G3 state high, and I explained how the current is being monitored through the designated pins such as CSOP and CSON, which is for the battery section, and CSIN and CSIP, which is for the adapter section, and all are passed through A, M on, and BM on, which is stand for the adapter monitoring current and the battery current monitoring, right? And this sent to the T2 chip, right? So as I said before, this is the T2 chip architecture with the type C, and the SMC is embedded inside of the T2 chip. So SMC reset, which is a part of the T2, but it is not used in this one. As you can see, NC charge underscore SMC underscore RST underscore L, which is not used. So after the the charging chip generates the PP bus G3 state high, and it detects it through the P bus pin, right? P bus and P bus power. The next thing it now needs to enable a regulator to turn on the PP3V3 RTC section to turn on the PMU IC, and that's the next step. So as you can see, after the main working conditions are okay, right, it will now release enable MVR. As you can see, it's renamed to charge underscore EN underscore MVR, and it's going out of the charging chip. All right, so let's copy the signal and see where it's coming from. Right, so it's charger underscore enable underscore MVR. Alright, so let's go to the first one, and here it is, and this is our the regulator. Alright, and it's called A1989, right? 3.3 volt G3 state high. This is the earliest voltage that is produced, which is similar to the PP 3.42 on the older Macs, right? PP 3.42, which is used to turn on the standby rails for the SMC. As you can see, this is using two coils in parallel, right? So you know that the current is very large. It's about 6 ampere maximum current. That's a very large current with a working frequency of 1.25 megahertz. So this is a very large output current, and it's renamed to PP3V3 underscore G3H underscore RTC underscore REG underscore R, and it is now renamed to another set of resistors here, which is a 0 ohm resistor, and it's been renamed to PP3V3 underscore G3H underscore RTC. Now there's, for this chip to produce this voltage, there's a set of working conditions that we must meet, and they are here. So first we have V in, we have V in 1, we have V in 2, we have an enable, right? We have a switch. This means that there's an integrated upper and lower MOSFET that's embedded inside of this chip, so you don't see any MOSFETs on the outside here, right? They're embedded inside. We have a voltage output detection, we have a power good, and we have a feedback. So this is a typical PWM IC, right? And as you know how a PWM chip works, first it gets supply, enable, then it will drive high, low, drive high, switch, drive low, switch, right? And then you get a rotation conduction, and then you get your full, you get the duty cycle. You get what I mean? See, this is a pulse width modulation, right, on the front end here of the coil, right? And the back end, you know, there's a smooth output, right? A rising edge. It's not a nice rising edge with the help of this capacitor here. So this capacitor is used to generate that smooth output voltage and keep it stable at 3.3 volts, right? And as you can see, the maximum current of output current is 6 ampere. Okay, so let me just clear. Alright, so this chip needs a working condition. Alright, so first we need V in. So V in, as you can know, is coming from V in, which is here, a PPVE underscore G3 underscore P3V3 G3 HRTC. Right, and coming through this resistor, it is being renamed to PPVI BPVin underscore G3H underscore P3V3 and G3 HRTC underscore R. This is how Apple names their name. They are very long, so you have to get used to it, how Apple rename their signal with by adding a letter at the end. So let's see where this voltage is coming from. It should be roughly 5 volts coming from the adapter, right? So here it is. So we have It's coming from so it's a PPV in underscore G3H underscore P3V3 G3H RTC, and we have another section here which is the same thing. Let's go down. Alright, so this is where it's coming from. Alright, so let's so this one is the same. Let's see if I was missing. Oh, here it is. So it's coming from PP bus underscore G3H. So this is 12 volts. After coming through the sensing resistor, right, this is a sensing circuit which is used to send individual voltages to sense all the voltages that are generated and sent to the SMC, right? So this is PP bus G3 state high sense, right? And this is used to sense the 12 volt rail. So if any short on the PP bus G3 state high set, it will detect it and it will tell the SMC that there's a short on that rail, so it should shut down the communication with the charging chip through the SM bus. Okay, so this is the sensing circuit. As you can see, there are other sensing signals, such as, let's see this one, right? Another PP bus G3 state high here. We have backlight current sensing. See, I sense backlight positive and negative, right? All that sensing current sensing information is sent to the SMC, right? We have, let's go down, we have SSD, right? PP bus I sense SSD NAND to detect the total current for the SSD. All right, all these information are sent to the SMC. Any one of these sensing circuits are not working properly, it can cause the system to move slow, right? And the CPU will drop its working frequency and the computer response will be slower. So this is a very important section here on the motherboard, which is the sensing circuit. Alright, so it's PP bus, so it's PP bus G3 state high, which is coming through this resistor. After coming through this 0.03 ohm voltage drop resistor, it will be renamed to PPV in underscore G3H underscore P3V3 underscore G3H. So it's coming from our 12 volts PP bus G3 state high. Alright, and when that gets V in, and it gets V in 1, right, this is a BJ package, and we get D, E1, F1, these are BJ package. So V in 1, V in 2 is input, right, and then we get the enable signal, right? So the 12 volts is coming here through these pins, and we get the enable, right, coming through the 0 ohm resistor. Then it will automatically starts to drive high at the internal gate, right? The lower MOSFET will start to drive, and we get the full duty cycle of pulse width modulation, right, on the front end of the coil. And then we have the output, which is going to be 3.3 volts, right? It's difficult to draw with the mouse. All right, so it's 3.3 volts, all right, with a current of 6 ampere output. And with the help of these filter capacitors, it will smooth out, so we get a nice rising edge on the oscilloscope. All right, so the output voltage is current coming through these two coil, which is connected in parallel, right? And it is a large output. So in time you see these two coils which is connected, that means that it's connected in parallel, so the current is going to be very large, right? And we also have a feedback pin, right? These are the feedback resistors, the R6912, R6913, R6910, and R6911, and there is a internal reference voltage for the output feedback, which is connected to feedback. V out is detecting the output voltage, right, of both. See, it's connected, and this is an input pin going back to this chip PWM IC to detect the output voltage, and the output voltage is internally calculated with the feedback, right? So the feedback, here is the formula. So V out is equal to 0.8 multiplied by 1 plus RA divided by RB, and the output voltage should be a constant of 3.384 volts, right? So any fault with these resistors, the output voltage will be a normal, right? And the voltage will be and the chip will just go in under voltage for our over voltage protection mode, right? So on the oscilloscope you get a waveform something like this, right? It indicates that there's a over voltage protection, or you can get something like this, rise and then just sudden falls, and this is known as an under voltage protection, depending on how you set your oscilloscope settings, right? So in PWM demo class I'll explain all of this, right? Once this output voltage is okay, there is no overcurrent, right, there's no under voltage, right, and there's no short circuit, then it will eventually release a power good signal. So but the power good signal is here, PG, so it's P3V3 G3H underscore RTC underscore power good, as you can see, and it is pulled up by a 100k resistor, and that 100k resistor is pulled up by PP3V3 underscore G3H underscore RTC underscore REG underscore R, and this is to confirm that the voltage are successfully generated and there's no over voltage, there's no overcurrent, and no under voltage, and the resistors here are intact, all are intact. Then the output, and then it will release the power good signal, indicating that everything is okay. Okay, so I'm going to go back to the diagram designer now, where I'm going to sketch out. So I'm going to pause the video and sketch this out and be back with you. I'll just sketch it out with you. Fast tone. Is that clear enough? No, not clear enough. Okay. Okay. U7000. How do we undo that? Alright, let's put it on the top. Alright, so let's go back to U7000 so I can. Alright, so we have P in first. Oh, I passed it. We have VDDP. And then we have VDDA. Right, so VDDPP powers VDDA through that resistor there. This is our resistor here. And okay, now we're going to generate. Let me carry down the diagram a little more so I can get some space. Okay. Now we have the so VDDP and VDDA is generated, then it will generate the gate Q1 to turn on the first MOSFET gate, right? Switching. I think I'll get this is a little wider. Okay. 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 Alright, so we're gonna get these MOSFETs now in. Start it right here. Alright, so it's two N MOSFETs. Alright, and this one other gate. Oops. Okay, carried on too much. I need upper canvas space. I'm gonna divide them in sections. So this is isolation and protection section. When I'm doing the standby, then I'll do it on a different canvas. Alright, so this one is the other gate, which is gate Q2, so gate Q1, right, for this one, first MOSFET, right, gate 2, right, we have gate Q2, and it is controlled by E1 pin, gate Q2. Good. Alright, so this one is connected to ground, as you can see on the schematic. See, this is the lower MOSFET, it's connected to ground, its source pin, and this drain pin for this MOSFET is connected to 5 volts, right? 5 volts, which is the PPDC in G3 state high. See, PPDC in GC state high, and then it is conducted, and then it go into boost mode because it's boosting from 5 volts to 12 volts, and I already showed you the waveform on the oscilloscope, and the boost is, and it's very dense with a very dense gate waveform on both gates, right? And it is ramping up the voltage to 12 volts, so it's in boost mode because it's taking from a lower voltage to a higher voltage, right? So the diode, this ground diode, this diode inside of the MOSFET, each time the ground diode hits the positive side of the negative side, sorry, of the diode, it forms a boost traps, just like for the backlight boost circuit. It boosts the voltage from 12 or 8 volts to 40 volts, so it can provide the backlight with the help of the coil. So the coil and the diode, right, when the switching takes place from the charging IC and this MOSFET being controlling these two MOSFETs, it is equivalent to the backlight boost circuit, and that technique, which is known as the 4-switch boost regulator circuit, right? So this is when each time the ground MOSFET here conducts, right, it hits the front end here of the coil, right? Right, it hits the front end here of the coil, right, and then the output voltage on this side, when these two MOSFET conduct again, then it will ramp the voltage to the 12.8 volts, right? So each time this rotation conduction occurs, right, it then generates that pulse width modulation and the duty cycle at a high frequency, and it creates that waveform, and that's how it is generated. Beautiful circuit, very powerful circuit. Okay. Alright, so okay, but this another part of this now is going to this part. Let me undo that. Should be a little higher. My mouse is alright, so I'm almost there. Good. Straight. Yeah. Difficult to select sometimes with the mouse. Let me just carry this in. Oops. Alright, there we go. I just want these two MOSFETs now, and I'll do the reverse. Alright, so these two MOSFETs over here, these MOSFETs now are in should I put them in a box? Alright, so this MOSFET is Q. Q70, Q7030. This Q7030 MOSFET. And these two are Q7040. Alright. Coil which is in the middle. So this is how the circuit should look on the schematic, but they put the coil, they separate the coil and put it above it, so it's gonna be a bit confusing. So this technique that I use, which is normally the way of oh, I used the wrong coil. So okay, there we go. All right, so this are the gates for these now. Oh, I should put the ground. I forgot the ground. First, the ground is here. Right, that MOSFET is connected to ground, and this one is also connected to ground. Good. And we have the gate here. Alright, so this one is Q7040, right, gate 1. Yeah, it's connected to here, and that's gate 4. Hold on, let me confirm. Gate 3, let's get gate 3 first. This is gate 3. Alright, so gate 3, which is the one is connected to ground, as you can see here, is gate 2, which is now gate 3. Right? Oh, I put the gate at the wrong place. Good. Okay, and gate 4. So this is, let me just name the gates before I forget. Alright, this is charger gate 1. And gate 1, which is right here. That's for gate 1. And gate 2, it's right here. Okay, good. Alright, and this is gate. Let me just finish draw this gate. So we have gate charger, gate 4. And gate 3. Can just call this gate 4. Alright, so okay, so this is our 4-switch boost regulator circuit. So let me just continue and generate the rest of the circuit to generate PP bus GD state high. And it's coming from here and then through the fuse, and let me just get the arrow at the end. Sorry. Alright, to system, and this is the fuse. Let me just borrow this fuse in since it's the same fuse. So this is F7000. Right, to generate our common point rail, which is 12.8 volts PP bus GT state high, and this is going to the system, and it's called PP bus. Right. Hey, haha. Alright, so let me paste again. Oops, undo. Didn't get anything. Oh, I see. Okay. Alright, and this is going to the system. Okay, so I've created this, so I'm gonna create the steps now first before I forget. Alright, so the steps is very important. Okay. Alright, so we put one. Step one. Okay. Alright, so step one, let me just give this a stroke color of blue and the A. And the text color of red. Okay, it doesn't really matter. Alright, so first step, the first step is this one, which is CC. The CC bus. Oh, I see why it didn't work. So if I move them individually, it doesn't move. Oh, okay. Let me just I did it wrong. That's what I should have done. Red. No. Still blue. Still blue. And red. Alright, there we go. Alright, so the first step, which is the CC bus. Alright, this is the first step. Pin up 1 and 2. Why this is the first step? It must establish the CC communication. So let's go back to U CD. This is a UB. Let's go back to the board view. Is this it? No. Yeah, here is it. It's U3200. Right, so as you can see, we have V bus. Right, so PP 20 volt underscore USB-C underscore X bus is coming to these pins of the U3200, which is a BJ package chip. This is a logic chip that speaks to the charger to boost the voltage from 5 to 20 volts with the SMC through the CC1 and CC2 lines. As you can see, we have two capacitors here. We normally check here for waveform, and I already showed you the waveform in the other video where the CC bus is communicating with the SMC, and the SMC is talking, and this chip now talks to the charger, and this is going to the adapter. This is going to the adapter interface, right? So CC1 and CC2, let's copy this and see where it's going. It's going to the DC jack. All right, so let's go down. No. All right, here we go. So USB C underscore X1 underscore XB underscore CC1, which is going to our connector, which is J3300. So you can see here it's coming from here, right, coming from the charger, and it's going to start directly to the logic chip to boost the voltage from 12 volts, from 5 volts to 20 volts, right? So this is the CC1 communication line, right? USB underscore C underscore Xbox underscore C1. As you can see, it's also passes the data, and that information is sent to the charger to tell the charger once the packet ready is okay and the power ready signal is activated, then it will tell the charger to boost this voltage from 5 to 20 volts, right? And this is USB connection to a MOSFET here. This is an N-channel MOSFET, and it's connected through by PP bus. Okay, so this is a protection circuit also. This is the isolation protection circuit. So PP bus underscore coming through this Zener diode, right? This is a Zener diode is connected to ground to protect the. It's called, another name for it is known as a transient suppressor diode, which is used as a clamping to protect the circuits from voltage spikes and EMI field interference and so forth. So that is what it does. So the negative side is connected to ground. As you can see, this is connected to a resistor, and the reason why it's connected to a resistor because of this N channel transistor, right? So if there's any overcurrent or any overvoltage occurring on this line, what will happen is that it will do a reverse breakdown conduction. But remember, this is a reverse breakdown conduction, and then it will reverse and keep this voltage stable at say 1 volt or 2 volts or whatever. So if this line exceeds its withstanding threshold breakdown value, then it will do a reverse conduction and stabilize this voltage right here and keep it at its designated voltage. So this is known as a transient suppressor diode. Okay, and then now it will control and act. It's basically acting as a protection, right? Let's go to the next line, and this is the other one for the USB. So each USB-C connector, for the 4 of them, each have this circuit for the protection, right? You have C1, C2, all of them have to pass through a certain protection to protect the chip so it doesn't burn. So as you can see, CC2 comes through this connection, right? CC1 is coming through this connection. This is to protect CC1 connection. This is used to protect CC2 connection, right? Let's go down. All right, see, USB CX connector support, right? And this is for one section. Oh, here's out of, so it's a total of 4 now. So it's 4 ports. It's 4 ports. So you need in all 4 of them, right? So it's 4. So one, this is USB CC1 here. See, USB CC1, right? USB CC2, another 1, another 2. So it's a total of 4 ports. So this is its protection, right? So this Zener diode is, this diode, as I said before, is a Zener diode, or you can call it a transient suppressor diode. These are very important diodes, right? It is used to protect from voltage spikes that induces the circuit, and to protect it if there's any over voltage or overcurrent happening due to EMI filter in electromagnetic interference. All right, as you can see, this gate is controlled by PP bus GT state high. It is 12 volts, right? The voltage at the gate, right, is greater than its source, so it will do a full conduction and send that information to the charging port or the DC jack, right? And this is acting as a current. See, we have a varistor here. This is measuring the temperature of the actual circuit. So this is a thermistor. As you can see, there's the resistor here with a sorry, the resistor here with a slash in it. This is a thermistor. So what is happening, that if the temperature increases, the resistance decreases. As you can see, it's a 100 ohm resistor, right? They put a 100 ohm resistor. It's acting as a thermistor to monitor the temperature, right? So as I said before, if the temperature increase, its resistance decreases, and it will tell, and it's also acting at the protection there to shut down if there's any over voltage, over current, because the current is along with the heat or the temperature, and current compensation and temperature compensation information is sent here, and this is also sending to the SMC. As you can see, it's a bidirectional communication, right? BI means a bidirectional communication, and it's going back and forth, right? So this is a very important and crucial circuit to understand. All right, so let's go back to where I was coming from. Right, so this is it. Yes, so let me just copy this, and that's this right here. And this is coming from CC1, CC2. So this connection must be established first, so the charger will immediately start to receive that packet ready to start communicating with the motherboard, so it can tell the charger how many voltage to output and the current, the designated current, right, to output in order to boost the voltage from 5 volts to 20 volts, right? So this is a data line. You should check here with oscilloscope only, right, for wave. If there's any fault on this line, then the 5 volts would not be established. You won't see the 5 volts on your whatever you use, your charging port support, that can tell you if it's boosting from 5 or it's actually detecting the 5 volts, right? So if there's any fault on the circuit, then you won't have 5 volts generated and the system won't be able to turn on, right? So this is 1, right? This is 2. Let me go back. All right. Okay, good. So this is one line for communication. So this is very important, right? And it is going to talk. So it's a bidirectional. So I have to put another arrow here. So it's a bidirectional communication. Okay. Let me see my time. Good. All right. So next step, right? 2. We have 3 years generating the PPDC in. No, 3. Sorry, we should check the gate. Right. Check both gates, and then 4 it will produce PPDC in underscore G3H. Right. Step 4. Right. And then step 5, you need to check P in. Okay, then 6, you need to check here PP VDDP powering VDDA. Then this is your next step. It will start to generate the gate voltages. Right. Oops. Alright, so check the gate 7. So I just put it in between for the both gates. Alright, and this one is 8. These 8, both gates. Alright, switching conduction locker. Right, and then you won't get any voltage here. You check here at the fuse F7000. This is 9. Right. So checking here, checking at the coil here will not generate. You will not find 12 volts here. Right, this basically a 4 buck boost switch regulator circuit. What it does is that each time the MOSFETs conducts, right? So this MOSFET comes in here. This MOSFET conduct, right? And then it's a rotation conduction. So this MOSFET conduct, the lower MOSFET conduct at this time, the upper MOSFET conduct, lower MOSFET conduction, and this is hitting the front end of the coil here. So that is going to create a very dense waveform, as you can see right here. And what it does is going into the boost mode, right? So it's called boost. So it's boosting from 5 to 12 volts. It's very difficult to draw with the mouse, right? So this is known as the boost mode. So you check here, you'll get wave. So you check here with your oscilloscope, right? You should get waveform at the front end here of the coil. Right? Right, so you check here, right? And then now what happened after this boosting, then on the front end, this MOSFET will be in a continuous conduction and you get a smooth output right here, because at this time this MOSFET is going to conduct first and then it will stop after a few milliseconds. Right, I didn't capture the wave. I'll have to show you in the next class how this circuit works when you're checking the oscilloscope. Right, and this each time the ground MOSFET here conducts, it creates that boost. So this is equivalent to a diode that is inside of this MOSFET. This MOSFET is the boost. Actually, when the boost is complete from this side, here, okay, right, from this side. I'm not getting my pointer. Let me see what's going on. Hold on. Am I in another mode? Alright, so this side here, right, after the boost, after the MOSFET start to switch and building up that pressure right here, right, this MOSFET will go into a continuous conduction, while this MOSFET will only have a waveform for about 200 milliseconds, then it will stop. Right, so each time this boost, it is boosting and getting us to 12 volts. Right, so this is equivalent to a diode that's inside of the circuit. So each time the negative end, it should be on the each time the negative end of the diode, right, each time the negative end of the diode gets that ground, right, the negative end of the diode gets that hit right here, it will automatically boost the voltage and it is going to generate the 12.8 volts. All right, it will generate the 12.8 volts. So that's how the circuit is working, and you get the 12 volts to power the system here. All right, so so after this circuit is okay, then we'll the VDD P bus VDD. So let's go back to U7000 on the schematic. Next one, oh, here is it. So U7000 here on the schematic. So this pin, which is P bus underscore power, as I said before, is going to detect the output that it is generated, right, which is connected to the charger chip. To detect the common point rail, which is here, 12 volts, and this is an input pin from here. Oh, it's in black. Sorry. Undo. Alright, so right, so it must detect that the voltage is generated, the 12.8 volts is generated for the PP bus before it can move to the next step. All right. Okay. All right, so the P bus is generated, P bus underscore power, and that is a feedback which is sent back to the charging chip that the 12 volts is generated, everything is okay. And then now it will detect this one, which is P bus, which is the current, which is going to detect the total current generated by the charging chip. Right, I don't think this is necessary. I won't draw it because it's already detecting here. This is the main one. Then the next thing we'll have enable VR, which is enable underscore MVR. Right, this is going to turn on our PWM chip that is going to create the PP3V3 underscore G3 underscore RTC. A. Didn't copy. Let's go again. this is going to turn on another regulator, and this is an output pin. Oops. That's coming from the charger, and it's called charger underscore en underscore nvr. Right, so this is 9, so this is 10, and this is 11. Alright, so I'm gonna get the small one. Alright, so as you can see, the circuit is now coming to how it's supposed to be when I break down the schematic and have it in a simpler way for you to understand. Alright, so this is how the technique I teach. So as I teach and I explain each circuit, then I sketch it out with the help of this tool, which is the diagram designer. Alright, I'm gonna just extend my canvas downwards. Alright, I need more space, so I'm gonna put this at about 450. Right there, so I get more space, so I can extend. So we're gonna go to this part now, to the PWM IC. Here it is. Right, and this is U6903. Oh, let's look for it on the bitmap. U6903. Oh, here we go. Right, it's also as I said, it's a BJ package. Right, so this is a BJ chip. Alright, U6903. So let's look for it on the physical scanned image. Alright, so let's zoom out. Oh, it's on the side. Okay, to the CPU section here, so it's right over here. Okay, here is it. This chip is also a glass chip, so you have to be careful when holding it with the tweezers. It can break, right, when the heat is applied. Alright, so this is this IC. This is the coils out here. These are the two coils that are going to generate PP3V3 underscore G3 RTC. So you should check these two coils. You should get 3.3 volts here. Right, so these coils are used with the help of these capacitors for filtration, and this is a typical PWM IC. Here we have the 19 volts, the 12 volts PP bus GT state high coming through these two. The measure here should get 12 volts, right? You measure here, you get 3.3 volts, right? And this is your PWM coils, which is going to output and is going to provide it to send to the PMU IC, right? So the PMU IC is right here. This is our PMU IC. It's going to power this IC, and this IC is going to, this is the power management logic controller chip, very powerful chip, and it's also a glass chip, so you should be very careful when handling this chip. Right, so this chip, as you can see, there's a lot of coils around it. Right, these are different power supplies that are going to power the T2. Okay, so let me just go back to the diagram designer. Let me get the image of this. Alright, let's get the fast one. It's not so clear, but let's work with it. Alright, so this is the chip, and we have our input. So first, I already explained this chip already, so I won't explain again. So we have V in 1, which is our input, 12.8 volts coming in. And PP bus is coming here. And this is called PP. No, it's coming to a resistor. All right, let me just copy. Right, and this is our resistor. And then it's gonna name. And it is being named to underscore R. Just an R. There we go. Right, and then it will we have the enable, which is coming from the charger chip, which is charge underscore en underscore vr. It's coming to the en pin. And it's going to another resistor. I think I'm going to need some space. Copy to here. I'm also completed. Okay, and then now we're going to have our output. Switch 1 and switch 2. And then we have our output coil. Oh, it should be a line. And then this will be your output. I'm not going to draw two coils, I'm just going to draw one and just connect it with this. Okay, and this is gonna call the output, which is here. And our power good. Alright, so this is gonna be 12. Oh, this is 11 already, so we have 11 here. So I'll just put it here, 11. So this is 11 still. Alright. No, this would be, yes, 11. Alright, this would be 12. Alright, and this is 13. Alright, and 14 are forward. Alright, so I'm gonna stop here for today. Alright, so I've completed this part so far. Alright, so in the next demo, we're gonna look at the T2 standby working conditions and the PMU IC working conditions and how it generates the different voltages, the power the T2 and the T2 working conditions, and how to check the T2 and some of the techniques and precautions that you should take when dealing with the T2 chip, because it's a double layer chip. It has an upper and a lower layer, right? And how to deal with it, especially when working with desoldering and maintenance of the T2 chip. All right, coming up in our next class. So okay, thanks for watching. Bye.